This video on velocity time graphs picks up from the previous video on distance time graphs. I'll be focusing on what the velocity time graph represents, how to interpret one, and also interpreting one in which an object moves at various speeds. Here, I have a velocity time graph for two different objects. You need to know that the gradient of the line is equal to acceleration. We know that the gradient of a straight line is equal to change in y over change in x. In this case, the change in y is equal to the change in velocity, and the change in x is equal to the change in time. A velocity changing over time is just equal to an acceleration. The steeper the line, the greater the acceleration or deceleration. If I pick a point in time, say here, the velocity of the object with the blue line increases by this amount. In the same amount of time, the velocity of the object with the dashed yellow line increases by this amount. So clearly, this object had a much greater acceleration. You'll often come across velocity time graphs that look like this. Just like with a distance time graph, different types of lines represent different things. A line curving upwards represents an increasing acceleration. In 25 seconds, the velocity of the object has increased by about 3 or 4 meters per second. After another 25 seconds, the object's velocity has increased by nearly 15 meters per second. So over time, the velocity of the object increases more and more. A flat line represents a constant velocity. The velocity of the object stays the same over time. Then we have another increasing acceleration, but this time not as great as the one at the start. And a diagonal straight line is a constant acceleration. The velocity of the object increases by the same amount every second. Then we have another constant velocity, and finally, any type of line, be it curved or straight, that has a negative gradient, in other words, the line is going downwards, shows a deceleration. If I were to ask you to calculate the acceleration of the object between 120 and 150 seconds, how would you go about doing it? Pause the video and have a go yourself. Right, so we know that the gradient, the change in y over the change in x, is equal to the acceleration. We want to know the acceleration in this region here. We read off the velocity for 120 seconds, and that comes out to be about 25 meters per second. And then do the same for 150 seconds, and that comes out to be 35 meters per second. That gives us a change in y of 10, and a change in x of 30, which is equal to 0.3 recurring. That rounds down to 0.33 meters per second squared, to two significant figures. Now, what if I were to ask you to calculate the distance that the object travelled between 120 seconds and 150 seconds? Pause the video and see if you can figure it out. We need to understand that the area underneath the line in a velocity time graph is equal to distance. We know that speed is equal to distance over time. The distance is equal to speed multiplied by time. We're only focusing in this region, so we need to find out the area under the line here. The area underneath it forms a compound shape, so we'll split it into two shapes, a triangle A and a rectangle B. The area of a triangle is half base times height, so 15 multiplied by 10, giving us 150 meters. The area of B is just its base multiplied by its height, so 30 multiplied by 25, giving us 750 meters. Totaling that up, we get a total distance of 900 meters. So between 120 seconds and 150 seconds, the object travelled 900 meters. You could also just count the squares underneath the line if you had a more complex line. And that concludes velocity time graphs. Just like with distance time graphs, in an exam you might be asked to describe a velocity time graph, so make sure to include things such as the time when the object was at its maximum velocity, so the highest point on the graph, the overall distance, so the whole area underneath the line, and areas where the object was accelerating or decelerating, and times when there was an increasing acceleration or deceleration.